What's going on, YouTube Nation? I'm your host, DJ Killer Keemstar, and let's get right into this project. So in today's episode, we're doing a little bit of calculus. You see right there, I Heart Calculus shirt, because this is what your fans wanted. You guys want calculus, I'm bringing for you calculus. We're doing a video on calculus, but I didn't know exactly what to incorporate, so I was like thinking for a little while, and I was like, dude, fetuses, placentas. That's calculus. So like for the past 100 years, since like the Great Depression and stuff, doctors have been coming together and they've been analyzing the composition of the fetus and placenta. And in fact, that's what our study is going to be based on today. This is published by G Forbes. Not Forbes the newspaper, completely different people. We're talking about G Forbes, and he was talking about he was analyzing the rate of growth for the placenta. And already, right off the bat, there's a big problem with this study. This study was done in 1981. I mean, you don't need Neil deGrasse Tyson to tell you that the technology they had back then is completely different than the technology we have today. So obviously, this study is going to be a little bit outdated, and we're going to get more into that at the end of the video. Nevertheless, Forbes still conducted the study from the growth rate and the placental growth. So he's calculating both growths, and you can see over here, you got up to 40 weeks for the placental growth, goes up and down like that. You've got the fetal growth, it goes wee and then wee to like 25 plus 40, that's like 65 weeks of him just getting the weight. Thing about the study, this study actually gives us the growth rate for the fetus and placenta, but it doesn't give us any other stuff that we want to like maybe know, like the weight itself and the inflection points. So I gathered along with my team. By the way, I have the best team ever. There's no better team than mine. I got the best people. Shout outs to you guys for helping me on this project. We got a team to analyze and dig up through all that jazz. So we're gonna go right into it. All right, so if you can see right over here, it says for a fetus is given in grams per day, and so is the placenta is given in grams a day. But if you take a look at the x-axis, this is for the y-axis, they're giving us two different measurements, but for the x-axis is given in weeks. So Forbes messed up over there. Now, of course, our amazing team had to correct this mistake by multiplying every single number by 7, changing the weeks into days. After observing a little bit, because we're trying to figure out whether this is in normal time or whether this is a derivative graph or a double derivative graph. So after doing some analyzing, we realized that this is giving us the growth rate. So this is the growth rate of the placenta up to week 40, which is birth, and it's giving us the fetus growth rate for the fetus. So we're like, that's growth rate. So obviously this is a W prime. So this is the derivative of the original function. And the reason why it's the derivative of the original function is because they're giving us the rate of growth. Alright, camera's like kind of broken in the front, so I apologize about that. But back to the point. As we grab these two figures in figure 1 and up there is going to be figure 2, we were able to place a trend line in a linear degree. So you see that trend line going whoosh, which is a linear trend line. As you can see here, we obtained our R squared value. Now our R squared value, this number over here, 0.124, is basically showing how accurate this trend line is. So to find out how accurate it is, you would have to multiply it by 100. So basically move the decimal twice and you get your percentage. So this one, you multiply it by 100, you get like 12.4%, which is like lower than Kim Jong-un's approval rating. That's real bad. That's real bad. Alright, so what does it mean to have such a low percentage? That means that this lineal trend line is actually a very, very bad fit for such a graph. I mean, our R squared, our trend line is in a linear way. So it's obviously going to be a bad fit because as you can see, the graph goes like that, but this one's going in a straight linear line. Alright, so to make it fit into everything, to get it into this state, basically before it was in this state, now to get into this state, to do that, we need to make our R squared, where is it? Right there. We need to make our R squared look a bit more accurate. How do we do that? What we did is we had to apply it to a 4th degree polynomial. So by doing that, not only do we get our equation for it, we got our equation for this line, we also get our R squared to 0.759, which multiplied by 100, That's like 75% accuracy, even better, 76% if you round up. That's even, and the other one is even better. This one, we went from 0.09, which is 0.9% accuracy, to this 0.905. You multiply that by 100, that's like 91% accuracy, which is really, really good. And we also get our equation for the placental growth rate. All right, so now that we got our equation finally, because they didn't give us the equation, we had to find it ourselves. We now need to do a little bit more digging. So what we're gonna do is we're gonna try to find the second derivative of the equation. Now, how do we do that? That's simple. Since we're already given the derivative from the first part, basically the first part is the derivative. All we need to do is take the derivative of that to get the second derivative. Again, apologies for camera, like I dropped it the other day and it just broke. But just to focus on the video, I promise I'll get a new camera. But to focus on the video, what's interesting here is that we actually have a graph for you. And this, we got these graphs using Desmos. By the way, shout out to Desmos. I love you guys. I couldn't do it without Desmos. Honestly, like, I failed calculus without Desmos. So Desmos is great. Anyways, we use Desmos to find what the graph of the second derivative would look like. And it looks, we zoomed it in a little bit. It looks a little bit like this. And we actually wound up finding our inflection points. I don't know if you could see it. Oh my God, it's beautiful, perfectly clear. You got our 3 inflection points, and this is for the fetal growth. All right, so this is for our second graph. This is for the placental growth. This is for the second derivative. And we got 1 inflection point at 119.497. And this is showing the speed of change. This is changing for the placental growth. Obviously not as much change of a placenta because not as much time. You know, after 30 weeks, it just goes out. You know, the baby is born, so the placental weight is not calculated anymore. All right, so at this point you might be wondering yourself, what does this all mean? Why do I care about this so much? Dude, the reason why this is important is because this represents the birth and change between pretermal and posternal in the placenta and fetus growth, dude. We've got our W prime, we've got our W prime prime, but we're missing a third something here. We're missing our original weight of a function itself. The reason why our W is so important is because the W is the original weight of the fetus and the placenta. I mean, we got the rate of change that they occur in, right? We got the changes, that's the second derivative. We got the change of the speed that we're going in. Those are with the inflection points, but we don't even know what the original weight is. So how do we find that? We use something known as the antiderivative. Antiderivative is opposite of derivative. Think of like Joker from The Dark Knight. No rules whatsoever. He goes his own way. And that's what the antiderivative is. While all the derivatives are going this way, antiderivative goes up. Alright, so to get the antiderivative, you basically have to work backwards from W prime all the way back to W. That's what we did for the placental growth, and that's what we did for the fetus growth. However, there's something missing over here, which is a constant for a fetus growth equation. We need a constant. Now, we're going to assume that our constant is 112. We're going to assume that X is 112. So we add 112 because we're assuming it's at 16 weeks, and 16 times 7 equals 112. So we plug in 112 for X and we solve for the constant. For our constant, we got like negative 5,250, and that's what our constant is for the fetus growth equation. Okay, now there's probably a section of you out there, just like the other people who say, why is this so important? There's probably a section of you saying, this isn't enough calculus, I want more. Well, guess what? You're gonna get more. Alright, so now here is a study looking at the effects of exercise on pregnancy. Now, if you want, we did a graph for it. Here's the graph for it. And we already skipped the previous step where we had to change our R squared. We decided to do it right away. R squared was 0.989. You're looking at a 98% accuracy for the R squared. Now, to get this info, all this info, and the R squared at 98 using a polynomial degree of 4, using all this info, you want more info. Do you ever wonder what it's like to have it at 0 weeks? Well, according to the graph, if you follow all the way down to 0 weeks, it looks like it's gonna hit around like 100 or so, 100 millimeters of gestation. But actually, no, it's just 0. You know why? It's pretty obvious, but you know, the graph is misleading. See, our model was not able to show that it's zero because our model assumes infinite continuity. So basically, this is just a small subsection of our model. The idea is that when you graph this, this will infinitely go this way, and this one will infinitely go this way, basically netting us a negative volume, which is impossible to have a negative volume. Just like you can't have pineapples on pizza. It's just not possible. Alright, gang, real talk over here. You know, this angle is all about the real talk. If we wish to compare the inflection points of the placental volume to that of the placental data from Forbes, we would have to find the inflection points by finding the equation for the placental volume and finding the W prime, where W double prime, where W prime prime would equal to 0. That would be your inflection point. You could also look at the original graph itself and estimate the inflection point by determining where there's a change in concavity. But the thing is, you can't compare the data directly because one of them is in grams and the other is in millimeters. Also, one of them is written in weeks and the other is written in days. You need to convert measurements back and forth. It's a lot of work, but you know that's what's got to be done to be able to compare it and stuff. But you know, with so much work into it, you're even talking about one of them in the 5th degree and the other in the 4th degree of polynomial. But even with all that work, your boy DJ Killer Keemstar pulled it through. We got you the data, we got your results. The placenta volume is around 30 degrees. That's where the inflection point is. And for the placental weight, the inflection point is around 28 weeks. Now, that's not exactly the same time that you're getting your inflection points, but it's a very similar time frame in which you're getting it. 28 weeks, 30 weeks, that's like 2 weeks off. That's like nothing. That's like 2 games of football for your favorite team. Alright, so we're coming near the end of the video, and you guys also requesting calculus. You also want us to make some medical conclusion and apply medical stuff to it. So before we jump into that, because you know we need to do different forms of jumping, we have to get a lab coat on. So once we get our lab coat, we become doctors, then we can jump into it. So, whoa. You got Dr. DJ Killer Keemstar in the room. So as I was saying before, now from a doctoral perspective, you're looking at a 25 to 30 week space of inflection points. One of them was at 28, the other one's 30. So I wouldn't say there's too much variation or difference there. Now, whether the study can be trusted or not, I mean, the weak congestion one can definitely be I don't see any problem with it. I could definitely see it being trusted. However, the real issue is with the Forbes one, because the Forbes one was actually graphed incorrectly. Like as I showed you guys earlier, it was graphed using the y-axis using grams per day, but the x-axis was shown in weeks, so it was actually graphed incorrectly, and that's why I don't trust the Forbes study. Furthermore, let's go back to what we were talking about in the beginning. Year 1981. It came out in 1981. We have much better technology, and I know because you're talking to a doctor. We have much better technology today than you did in 1980. So obviously you're gonna get different results in fact. So I'm not sure that the study that Forbes did, maybe it was accurate then, but I don't know about how accurate it's being now. Finally, the last touch-up is of course the inflection points. And I think it's pretty clear that the inflection points for the fetal mass will be completely different from the inflection points from the placental mass. So what gives? Well, as a doctor, Dr. DJ Killer Keemstar, I'll give you the answer to that. The inflection points occur at different times. The reason why that occurs is because their processes of growth is different. If you remember the first graph, placental data is only existent until week 40. That's because that's when the baby is born. So once the baby is born, you can't measure the placental data anymore. However, for the baby, you could still measure the data they measured it up to 65 weeks. So you're getting different windows of time period. So you're getting different inflection points because you're getting the placental one, which goes up and down and completely stops at week 40. You're getting a fetus one, which goes up and down all the way to week 65. And that's why there are different inflection points for the fetal mass, the fetal growth and placental growth and placental weight. Enjoyed the video. I worked really hard on it. Shout out to my team for helping me out. You guys are like the best. Shout out to Desmos. Desmos was great. And yeah, Dr. DJ Killer Keemstar signing out.